So this is a topic that deals with what we're dealing with right now, like the measurements and everything. But we mainly use this in our labs that we have to do in our reports. So even though we're going to kind of go through it and test you on it now, it's going to somewhat only really reappear again moving forward into things like formal lab reports and stuff like that. But it is a very important topic. I like it better than significant figures as far as keeping track of how well you know what you know. So keeping in mind, remember, every measurement that we make, it's just an estimate at some point. We have tools that are really good to a certain point, but we can't be perfect with any of our measurements. They're only so good. And so therefore we have something called uncertainty in our measurements. So even the ruler that goes down to millimeters, we are still estimating however millimeters for a certain object, like what its length would be. So we have to keep track of all that. Significant figures attempts to do this somewhat, but I think these uncertainties actually do a little bit better job. They tend to be a little bit more confusing to use in the beginning, but I think they're a little bit better at the whole thing in general. So anyway, we'll go through them today and then give you some time to work on them. Don't feel too bad, if at first you're struggling a little bit, but once you get them, then they're not usually too bad. So, all right. So here are the two main types of uncertainties. Oops, let me get myself out of the way here. Here are the two main types of uncertainties that you're really going to deal with. One of them is digital tools. So when you're looking up stuff, we're going to have some digital thermometers, digital scales. Those are probably your two main things. Has a readout, like you see this thing down here in the corner. Or the bottom of the screen, there's a digital display, and those are maybe the easiest ones to get the uncertainty. So what's the uncertainty on this? It's reading 126.4, but what's the uncertainty? What do I know? What am I estimating? And really the estimate is in that last digit. So whatever we do is we look at what the readout is, and we pick a plus or minus 0.01 or 1 in the last number. So if you look at here, if the readout was 5.00, the last digit is that hundredths place. So I put a 1 in the hundredths place, meaning that current one, if I was to write it down, let's just say that's a scale, so it's measuring in grams. I would say 5.00, that's my readout, and that last zero is kind of an estimate, plus or minus 0.01 grams. What that means is that there is some true value of mass of whatever I just measured, but I don't know exactly what it is. I can't, because my scale is only so good, and any scale that we make as humans can only be so good. So that means the true value, whatever it is between 5.01 and 4.99. So somewhere in that range. That's a pretty good range depending on what we're doing. It's a pretty awful range depending on what we're doing. So it really, again, depends on the whole context. Typically in the lab that we deal with in class, that's a pretty good range for what we're doing. Okay. So if it's digital, just put a 1 in that last digital readout. So plus or minus 0.01 in the hundredth place in this case. The other types of tools that you're going to run into are tools with graduations. So graduations are lines like this, and you're looking to see what line is something on. So the graduated cylinder is a very common example of that. We're going to be dealing with things called burettes, which have graduations. The other thing you might see are thermometers. We have some digital thermometers that we typically use, but the run-of-the-mill thermometer with the lines on it, then you're using something with graduation. And so this one's a little trickier, because what you have to do is figure out what each line is, each graduation is. So if I didn't know, let me just guess. Let's say I didn't know that each line was a 1 in this graduated cylinder. I'm going to guess. Let's say each line is 2. Why not? So I'm going to start at the 40 and guess. I'd be at 2, 4, 6, 8, 10. I'd already be at 50 right here in this line, and I can't be. 50's not there. So I've got to make another guess. I'm going to guess that each line is 1. 40, 1, 2, 3, 4, 5, 6, 7, 8, 9, 50. That makes it perfect with the next number up. My guess was right. So in this case, each graduation is 1. Well, for the uncertainty, we always go half a graduation. So every line is 1. That means my uncertainty is a half of that. So which would be in this case 0.5 milliliters if my uncertainty is 1 milliliter. And I have a couple more examples to show you that a little bit later. Okay, so here's what I want you to do. Here's two digital tools. And I am going to show you what the uncertainty is here in a second. But maybe pause or just take a second and think, what would the uncertainty be on that scale on the left? And we'll move that one away. Okay, here it goes. Here's the answer. Your uncertainty would be plus or minus 0.01 grams. The reason being the last digit is there on the hundredths place, so I put a 1 in the 100th place. Okay, pause now, because then tell me, well, pause after I say this, what's the uncertainty on that scale? How would I report it if I was reading this 126.4, whatever object's on there? Pause now. All right, here's your answer. The uncertainty is 0.1. Remember, the 4 now is the estimate. It's the 10th place, so I would say plus or minus 0.1. So if I was actually going to write, what does the scale say? Take the measurement, assuming it's grams. It'd be 126.4 plus or minus 0.1 grams. Okay, how about these? Now we've got some stuff with graduations. Okay, first take the graduated cylinder on the left. Pause the video and see what you get. All right, here comes the answer. So if we're taking a look at this, I have to guess, each line. Remember, this is the one that I actually showed you just a little bit ago. Each line is 1. If I guess that, I count 1, 41, 2, 3, 4, 45, 6, 7, 8, 9, 50. So that means my guess of 1 is right, but the uncertainty is always half of that graduation, so half milliliters. Now here's key. When I report this, notice how I had to report, by the way, it's 43, because the bottom of that meniscus is on the 41, 2, 3 line right there. So I repeat 43, but I can't write this. So I'm going to write this in red, what you can't do. 43 plus or minus 0.5. This is not okay, because it's not in a formal way of speaking, because the decimal place on the uncertainty is in the 10th place. I need to have my digits here also being to match those places. And down here, which I can't point because it's too far on the bottom, but down here, you can see that I do 43, I end at the 1's place, and my uncertainty ends at the 10th place, so I can't do that. Okay, look at the next graduated cylinder. This one's a little trickier. See if you can not only get the uncertainty like this, but also how would you write it? How would it be written? So pause now. Okay, here comes the answer. I'll move this out of the way. Let's take a look at what we got. If I guessed, every line, let's say, is 1/2, so this is at the 20 mark. So half 21, half 22, half 23, half 24, half 25. My guess of 1/2 is correct. If I don't hit that at the right spot, re-guess, try again. So that means each line is a half a milliliter. That means my uncertainty then is 0.25. So already then I would know this part. Like whatever it is has to be plus or minus 0.25. Make sure, let's see if I read this. 20.5, 21, 21.5 right there on that line. But don't put 21.5. Make sure you have that decimal point there. This one went to the 100th place, so this has to also go to the 100th place. And by the way, these are all called absolute uncertainties. So there's another thing called percent uncertainties. And these two things, oops, I don't mean to do that. These two things, this here, is exactly the same as this here. This right here is exactly the same as this here. Now I have some formulas for you on the bottom, but if you're just trying to write down formulas and always use those, I think you're not really going to understand what exactly you're doing. I think you already know how to convert between absolute uncertainties and percents, but maybe just don't realize that you know how to do it. So, for instance, going from absolute to percent, if I want to do something like that, it's like when you figure out your percentage score on a test or something. Let's say we have a 25-point exam and you scored 1 out of 25 and you want to know, well, what's my percentage? What am I going to do? I'm going to take the 1 that I got out of the total 25 grams, right? This was the uncertainty. This was the actual measured value. And we're trying to figure out, well, what percentage is 1 out of 25? So 1 divided by 25, and then we times that by 100 to put in a percent, and I'm going to get 4%. Hence why you end up with that number there. Okay, what if I need to go backwards? What if I actually have the percent uncertainty? And I want to figure out what the absolute uncertainty is. So this one's saying, hey, it's 30.5 milliliters plus or minus 0.33% of this actual value. So what I would have to do for that one is just like doing the opposite. And you may be seeing something like this in math. Okay, so basically I can do 0.33, but I have to divide it by 100 because I have to get my numbers out of percents. And I would just times it by that max value, which was 30.5. What is 0.33% of 30.5? And that answer would be 0.1 would be my answer. And that's really all it is. So I would be going back and forth between uncertainty, absolute uncertainty rather, and percent uncertainty. The only thing I got to watch out for is I need to make sure that when I get to absolutes, and this is only for absolutes, not for percent uncertainties, that whatever decimal place I have for the absolute uncertainty, it has to match the decimal places in that actual answer. Make sure you line those up. All right. So here's just some things to say, well, how do I write them down, right? How do I know how to display this? And this is mainly going to be in reports. I think the percent uncertainties are probably the easier because there's really no hard and fast rule. So if you were to do this, right, and say, okay, what's the percent uncertainty? This is 5 divided by 90 times 100. Here's what your calculator is going to spit out. So what do I write down? Typically what IB says, and this is just them, as long as you're consistent in your report, it doesn't really matter. But typically what they say is that you should keep it to one significant figure. So one significant figure, okay, the 5. Next thing tells this 5 here to round up, so I say plus or minus 6. To be honest, if you wrote it as 90.0 plus or minus 5.6, and you kept that consistent throughout your report, that's fine. As long as things look nice, you're consistent, you got a reason, great. There's no hard and fast rule exactly. This wouldn't look very good, so I wouldn't do that. But 6, 5.6, whatever. We're kind of easy on the percentage one. When you go the other way, let's say we said, okay, we got 52.3 plus or minus 0.3%, and I want to get that into absolute. So I got to divide the 0.3 by 100, times it by the max, and this is what my calculator spits out. Well, my number had to the 10th place, so I need to make sure I keep this to the 10th place. That 0.1, okay, I go one more digit further, and the 5 tells that 1 to round up to 0.2. So keeping those decimal places lined up. When we have an absolute uncertainty, the decimal places have to line up. When it's a percentage, well, you can kind of choose what you want to do with that. As long as you're consistent, and it looks nice. All right, so these were just some of the rules that I just mentioned to you. And just sorry, this was an arrow; it just didn't carry over. Okay, so these are just some guidelines for IB for percent uncertainties. Use one significant figure if the percentage is greater or equal to 2%. If it's less than 2%, they suggest use 2 sig figs. Now, if you want to use 2 sig figs when it's a little bit bigger than 2%, that's up to you. But, use whatever you think looks nice and gets the job done. I like the 2, if you're not sure, just always use 2 sig figs on the percents, and then you're good, no matter what. All right, so here's where the calculations and stuff start to get interesting, and then we're going to eventually want to use something called a spreadsheet, really, to make this stuff work. Okay, propagating uncertainties. How are we going to make this work? Well, I guess I'll just come up with some questions that can make this work. So let me just create some questions here. Let's say that we take a temperature reading and using a digital thermometer, and it read 20.0 plus or minus 0.1 degrees Celsius. And then I heat this water up. That's what its original temperature was. And let's say I heat it up again. So let's say that's my temperature initial. I'll put TI for temperature initial. And I can't seem to make an equal sign on here. There we go. And let's say I heat the water up, and for some reason I choose a different thermometer to measure the new temperature. So I'll go TF for final temperature. And let's say that it's 30.00 Now let's not do that. Let's do 30.0 plus or minus, but this different thermometer has a higher uncertainty. Let's go with 0.2 degrees Celsius. The question is, what's the temperature change? So to actually get the temperature change, that part probably isn't terribly difficult for you. The temperature change, I'll just put it like a triangle T, is going to be 30.0 minus 20.0, and I'm going to get, keeping decimal place rules, 10.0 degrees Celsius. That part's not usually the tricky part for most people. The tricky part comes in, what do I put on the plus or minus? Okay, well, you can see way up here, for addition or subtraction, which I just did subtraction, I'm going to always add the absolute uncertainties. So here's my absolute uncertainty here. Here's my absolute uncertainty here. 0.1 plus 0.2 is going to equal, so 0.1 plus 0.2 is going to equal 0.3. So I would report this one as 10.0 plus or minus 0.3 degrees Celsius, meaning that the difference in temperatures between the water when it was hot and when it was cold is 10 degrees, but I have an uncertainty of 0.3 degrees based on my thermometers not being the best. So that temperature change could be as high as 10.3 degrees, and it could be as low as 9.7 degrees. Anywhere in between there is the actual true temperature change. That's what I'm reporting for this. So that one's not usually too bad. But notice if you do division or multiplication, you still add uncertainties. It's got to be a percentage uncertainty. So, I could make this really easy, but why not go with a more difficult one? Because I think you'd probably get the easy one. So let me make up a multiplication division type question. Let's say I'm doing something with, I don't know, speed. The distance that someone traveled, let's say, was 10.0 meters plus or minus 0.1. Sorry, I should have put the meters at the end there. And let's say the time. The time it took them to do this, let's say it was 5.0 plus or minus 0.1 second. And the question is, well, what's the speed? Okay, and I'll just tell you that speed is going to equal distance divided by time. So to get the actual answer for the overall thing here, this wouldn't be terribly tricky. It would just be 10.0 divided meters divided by 5.0 seconds. My units don't cancel, and I'm going to get 2.0. 2 sig figs on the bottom. There's 3 on top. 2 sig figs is the lower one, so 2 here. I'm going to get 2.0 meters per second. And that's all good until I got to throw on the uncertainties. So I can't just add 0.1 and 0.1 because those are absolute uncertainties. To make this one work, I just did division. I have to use the percent uncertainties. So, okay, before I can do this, I need to figure out some percentage uncertainties here. So for this one, well, I got to figure out what percent is 0.1 out of 10. So 0.1 over 10 times 100. That's the same as saying 1 out of 100, so I believe that is going to be 1% uncertainty on that measurement. And on this one, it's going to be 0.1 over 5 times 100. And that's actually going to be 2%. And so if I were to add those two percentages, I would have 1% plus 2%. That's going to equal 3%. So I could report this as 2.0 meters per second plus or minus 3% of the value. And if you wanted to, you could then convert this back to absolute. If you wanted, you could say, okay, well, what's 3% of 2? Do 3 divided by 100 times 2 and go back that way. Actually, when I switch inks and just do that for you real quick so at least you can see it. So, what I have in the box so far is fine. But if I wanted to, I could switch it to, this gets tedious, 3 over 100. That's my percentages, right? Times it by 2. Let's see what I end up getting there. Let me pause and do it in my calculator. Okay, so when I do that, I get 0.06. And so I want to make sure that my decimal places line up. I'm not going to change my original answer here, so, which is in the 10th place for 2.0. So I'm going to round up 0.06 to 0.1. And that way it'll be in the correct spot. Sorry, there's a little decimal point there. Okay, so these things can get worse and worse. And this might be an example of something where that actually happens. Graduated cylinder with uncertainty 0.5 milliliters is filled with water to 10.0 milliliters. Then we add the rock to the cylinder and the water level rises to 17. The mass of the dry rock is 50 plus or minus 0.1. What is the density of the rock in grams per milliliter? All right, well, here we go. I'm going to run through this one for you. Okay, first things first. I need to figure out what is the volume of this rock. So it is water displacement. So the volume I'll put of the R of the rock is 17.0. And that was plus or minus 0.5. And we're going to subtract from that 10.0 plus or minus 0.5. So my answer for that volume is 17 minus 10 gives me 7.0. And for my uncertainties, you always add the uncertainties. In this case, since I did subtraction here, I need to add the absolutes. So we're going to get 1.0 milliliters for the volume of this rock. Well, luckily I already know the mass of the rock right here. But the problem is with density, I'm going to have to do some division. So I know that I need to get these into percentages. So let me go ahead and do that. So for the volume, I'm going to do 1 divided by 7 times 100. And let me pause real quick so I can type that in a calculator. Okay, so I did it, and I get 14.3%. And just to let you know, I also did this for the 50 in the 0.1. So I did 0.1 divided by 50, and I get 0.2%. So that's going to be important, because when I want to do the density of this, it's going to equal mass over volume, which is going to equal 50.0 plus or minus. In this case, it's going to be, I'm going to use the percentage, 0.2%. And I'm going to divide that by 7.0 plus or minus 14.3%. And now you might look at this and say, well, you didn't round that to 2 sig figs or whatever. I kept a little more because I'm in the middle of a calculation. I can finalize my answer and get all that stuff figured out at that point. All right, so let me just do a calculator here. I'm going to pause and do 50 divided by 7 and see what I get. Okay, my calculator spit out like a 7.1428, whatever. I need to have 2 significant figures because there's 2 in the 7.0. So I have 7.14, so that rounds to 7.1 plus or minus, and now I'm going to add the percents. And so it looks like I would be adding 0.2 plus 14.3, so I get 14.5. I'm going to round that to at least 15%, I think would be a good number. But if I wanted to use the rules that IB is sort of suggesting, well, then to one significant figure, that would actually round to 20%. And so here's where you might sit there and say, well, geez, their rules seem a little bit strict on that. And this is where you can use your judgment if you want. Oh, by the way, geez, look at me. I didn't even use units. I should have grams and milliliters here. This is in grams per milliliters. Here's where you can use your judgment and think, well, I think I can do plus or minus 15, and that's a good number. And if it is, then go for it. Then that's fine. But I just kind of went with their suggestions and made it really conservative of an estimate to plus or minus 20%. Okay, last thing. I get these questions here. What about this? What do we do when we're converting uncertainties? How do I do that? So that's actually not too bad. Let's say I've got 20 milliliters and I want to convert that to liters, right? Well, you do 20 milliliters and 1,000 milliliters equals, per 1 liter, and I get 0.02 liters for my answer. What if I have an uncertainty on that sort of thing? What do I do? What if instead, let me just erase this a little bit. What if instead this was 20 plus or minus 1 milliliter, and we want to convert that to liters? Well, you do the exact same thing I just did, but I have to just separately take that 1 milliliter uncertainty, And I would also do 1,000 milliliters on it per 1 liter. That's going to be 0.001 liter. And now you kind of have to figure out, based on the question, what you're going to do here. 0.02, I'll probably just do this, 0 plus or minus 0.001 liters. So you would just convert the uncertainty exactly the same as you would the normal number. You just have to do an extra question on that one. Now, how about this? How come you threw the 0 on here? It depends on the situation of that. Because of just a quick calculation, and I really wasn't paying much attention to my sig figs and stuff, I just tossed a 0 on here to make sure that they line up. But that might not be the right answer. You got to think of the situation where, oh yeah, I think I'm accurate enough where I can toss that 0 on, versus, okay, well then I'd have to maybe round this to plus or minus 0, right? If based on that. But okay, the main thing I want you to get out of this one is, what about the process? What do I do? How about averaging uncertainties? I want to say this one because you're going to like the answer probably on that one. If you have average of numbers, please just average their uncertainties. So for instance, let's say I've got 3 measurements. Let's do it here. Oh, that's a really bad looking arrow, isn't it? Okay, let's say I've got 3 numbers. 5 plus or minus 1. And I've got another measurement that's 5 plus or minus 2. And I've got a third measurement that's 5 plus or minus 3. And I want the average value of my 3 measurements. Well, the average value, is going to equal 5, right? What's going to be my average uncertainty? Well, when you're averaging, you're actually not taking a measurement and building off it with another calculation to make things worse. You're actually kind of making things a little bit more, I don't want to say better, I don't know if that's the right word, but you're kind of like keeping it as a, I don't know, just looking at it a little bit better, maybe. Let's put it that way. And so you would just average your uncertainties as well. And so what I do here, just like you've always done averages, 1 plus 2 plus 3. There's 3 numbers there, divide by 3, and I would get the answer 2. And so that would be the average that you use. All right, so that is it for uncertainties. It's quite a bit to throw at you, I know, but as you go through it and do it, it tends to be a little easier when you figure it out. And even though we're going to go with this through our exam, our unit, and our exam for this, then we pretty much just deal with this on sort of formal reports.